The goal for today is to understand how we could get a meaningful number when we are asking for the number of lines in quartics. Let's first talk about what that would mean. First off, let's talk about this function smooth polynomial. This is a function which you do not have unless you did the exercise last week. So this just generates a polynomial which gives me a smooth surface inside of P3. So it takes a polynomial ring and generates a polynomial of degree here. This is my home-cooked function. So that's what we got here. You see, smooth polynomial gives me something sparse and I can modify it. I can increase the number of monomials by editing this sparse variable, so the sparse parameter. We talked about how to define functions with parameters. I encourage you to write your own polynomial generating function like this one. What's important is that the surface corresponding to f is always smooth. Okay, so if you don't have one such function, I encourage you to stop the video and write one yourself as you follow along. And then another homework was to write a function that counts the lines inside a surface. So now I wrote a function called countLines. It takes in a polynomial f and counts the number of lines inside the surface corresponding to f, the zero locus of f. For example, this quartic has 1 line. And this is what I meant when we were talking about the number of lines on a given quartic surface being rather ill-defined. It jumped in this 10 experiments from 4 to 7 to 18, and we have also 5 and 16 in there. And what's happening is that there are still more lines than anyone who knows the answer would expect. So one standard answer is that the generic quartic should have no lines. And my polynomials were not generic because they were sparse. By default, they come with 5 monomials. So now I change this. I say use 35 monomials. That's the maximum number of monomials of degree 4 in 4 variables. And now our 10 experiments really did find random polynomials giving quartics with no lines in them. So these zeros are the number of lines. At least that agrees with our expectation that with probability 1, we should hit a quartic with no lines whatsoever. And then strange things happen, as they tend to do, when you have fewer monomials. So for example, 10 monomials, still larger than 5 and still a large space, but we nevertheless get 1, 2, 3, 4 examples, and amongst 10 examples, that's a 40% hit of having more than 0 lines. But nevertheless, these numbers are unpredictable, and we want to first observe what's happening, why we get 0 solutions, and check whether or not we can increase this count. We change something so that we get a well-defined count. Let me recall how we counted lines, at least on an affine chart of the Grassmannian. So I start with a polynomial f. I define a 4-dimensional space corresponding to this affine chart of the Grassmannian. And then I have my P1, sort of universal P1 over this affine chart, parameterizing the lines with coordinates uv. And then I plugged in to f the parameterized line with variable aij's. And then this is a polynomial of degree 4 in homogeneous of degree 4 in variables uv, and I read the coefficients. And I'm constructing the ideal generated by these coefficients. For example, if I were to compute, let's say up to here, we see that this ideal has 5 generators. I mean, these are the generators that I have already given to it, because a homogeneous polynomial of degree 4 in uv has 5 coefficients. Coefficient of the constant term, so to speak, and the highest degree term. And therein lies the problem that my space where these polynomials lives is 4-dimensional. And I have 5 polynomials, so you could expect that if these 5 polynomials were somehow random enough, then I would get no solutions. So each polynomial cuts down the dimension by 1. 5 things cut down the dimension to -1 basically, so there's no solutions. But, as it does happen, when f is very special, then these polynomials in I somehow are configured in such a way that they have a common intersection point. This is not something you expect from a random polynomial system, but this is not random. F is very small, it has a line, and it conspires to make these polynomials have a solution. Except when I take a random enough f, and then there are indeed no solutions. Okay, so what to do here is, the problem is clear. I will always have 5 equations, and I will have 4 variables. So the point is to increase the number of variables. If I were to have 5 equations and 5 variables, then I expect solutions, and the number of solutions, perhaps just like in the case of cubics, would be constant. And how to increase the variables is this, that this is a system of equations. I want to introduce a parameter into this system of equations so that as they vary, every now and then they intersect and they have a common solution. And the way to do it is to choose, well, the source is a polynomial, so I'm going to introduce a parameter into the source. So I'm going to make my quartics vary. To begin varying our quartic, what I want to do is to generate 2 random quartics, but for the sake of simplicity, to get a clean answer, I'm going to make sure that my second quartic has no lines. So what I do is I generate a quartic, I display it over here, I count its lines, I don't care how many lines it has, and then I generate my second quartic until it has no lines. And I'm going to take the pencil of quartics spanned by h and g. So what I've done is that I added to my affine space of the Grassmannian another variable t. This I had to do for basically technical reasons or for what to come. But in any case, I wanted a 5-dimensional ambient space. So I introduced a 5th variable, t. And then I create a polynomial ring x, y, z, w with capitalized letters over this 5-dimensional polynomial ring. So these will be its coefficients. Again, you have to do it like this for Magma to be able to compute what we want to compute. And then finally, I coerce my polynomial g in 4 variables into this polynomial ring with 4 variables. So little x, y, z is replaced with capital x, y, z, w. Nothing new happening here. Remember, this exclamation mark forces this g to lie in this polynomial ring. Same here with rth, except h I multiply with t. So now I have a family of quartics, because when t equals 0, I get g. When t equals 1, I get g plus h, and that kind of thing. And let's look at what this looks like. I forgot to execute this command. Okay, so let's look at this. We have generated a g. This g has 1 line. We generated an h. This by construction has 0 lines. And then I constructed f to be the sum of g and h with h multiplied by t. We also ended up capitalizing x, y, z, w, but here you see the parameter in the coefficients t here. Okay, so far nothing strange except for the construction of the polynomial ring. And I did this because I want to replicate the evaluation of f inside of this universal line. Okay, then I construct my universal P1. So this is a P1 with UV variables, but it lives over T. And then I'm constructing the ideal by reading the coefficients of f evaluated at my universal line. Now f also has its t's and its coefficients. I've introduced aij's. When I read the coefficients, I'm going to get 5 equations in 5 variables. So maybe let's look at this now. There are 5 elements here. Count the commas, 1, 2, 3, 4, 5. And then there are t's and aij's. Very good. Now let's see what kind of scheme this cuts out. For example, we can look at dimension of x. And here we have our first very important lesson. So this computation got stuck because I forgot to do something very important and rather subtle. Let's see, I killed this computation. Now let's go back and fix the problem. There is no mathematical problem, but there's a computational problem. So here, when you're creating a polynomial ring, if you're going to do calculations like computing the dimensions of subschemes or their degree or something, it's really bad to construct your polynomial ring without further description in Magma. So there's something called a monomial ordering. Maybe we will talk about this in next weeks. So by default, it takes the lexicographic monomial ordering. You're supposed to take the Grevlex monomial ordering for calculations to be much, much faster. For example, I think I got stuck at dimension of x. So let's see whether or not this will end. Okay, after many seconds of waiting, it did terminate. The dimension is 0. First of all, x is not empty, and it's just a collection of points. And let's see what the degree is. Okay, so the degree is 319. Let's try a few more things. Okay, let's repeat this construction a few more times, randomly generating G and H, and let's see what the degree is that we get. Okay, so after about 18 seconds of waiting, we see that the degree is 320. Let's do that again. Okay, now we waited 12 seconds and I have a degree of 317. Maybe I try once more. Okay, another 19 seconds of my life has passed away, and now we have a degree 320 set. What's interesting here, and what should have been observed, is that these numbers are very close to one another. They're not wildly fluctuating like they used to with a random quartic. So these random pencils of quartics are generating essentially the same number of lines within the family. And well, the number does change, but you can imagine why this is changing. I'm just using one affine chart of the Grassmanni. Some of the lines end up lying in the complement of this affine chart, and therefore we get this discrepancy. So the correct answer here is indeed that this degree within the entirety of the Grassmanni would have been 320 on the nose, always for every f and g, provided, well, I should have said, provided the general member does not have a line inside of it. So that's why I constructed H to have no lines in it. And another advantage of this is that one of the lines is not at infinity. That's also why it was important that H had no lines, but G could have had lines. Okay, at this point, you can try to remove the Grevlex here at your own peril. It takes a long time. See whether or not it will terminate at your computer. And you can read about monomial orderings on Magma and maybe try to figure out what they do. Another thing is try playing around with your polynomial generator. Generate random polynomials, cook up this function, basically this procedure for yourself, and see what happens when you ask for the degree. So if you increase the sparsity, so let's say if I were to go to 20 here, so now I have 20 monomials in my f and h. Let's see if this calculation terminates, and if it does, what we get. Okay, so this is a very good sign. I've made my h and g much more random by increasing the number of monomials. And now I got 320 on the nose, and now I only had to wait 26 seconds. I'll do this again for you, and we should get 320 again. Okay, very good. We got 320 again. So this is very convincing that indeed the number of lines inside of a general pencil of quartics should be 320. So what I want to do next is to find which of these quartics, so in my pencil of quartics, which I represented by f, which has a parameter t inside it, which quartics have lines inside of them. This is what I want to find first. And to do this, we will have to learn a few basic operations, and then we should find a univariate polynomial in t whose roots give me those special values of t for which this f specializes to a quartic with a line inside of it. That's what we will do in the next section.